Swayam Prabha. Digital India. Educated India.
This is one topic, which is really is in the center of algorithms and mathematics, which has such powerful applications, right? It has made, these people who have discovered have made millions of dollars and made companies, and every day you are all, when you are using your mobile or, logging into some secure websites, there is something behind it. There is some version of engineered RSA behind it. So, you all know what cryptography is, right? What is cryptography? What do you study about? What? I have not heard. People don't know cryptography? Okay, you don't know what is the precise way of saying it. That's fine. I understand. Just say something which you know. What is cryptography? Right. So somehow, you all, I'm sure you do it in SMS between your friends. You want to make sure your parents don't want to know this. Then you have some cryptic messages you will convey, right? So cryptography is just basically study or science of secret communication, and this was prevalent and necessary in wars, and that's how the whole thing got started. But today, your credit card transaction, your banking transaction, everything requires secret communication, and so it is it has found a lot more use than just in the wartime, right? So the thing I'm going to talk about is public key cryptography. And it is specifically RSA. It stands for three authors: Rivest, Shamir and Edelman. Okay. All three of them won Turing Award for this work. And the key thing is it's sort of public key. Okay. So let me just, first of all, I don't work in this area, so cryptography is a big ocean. I know very little, so I'm going to just tell you what I know, particularly the math behind the math and computer science aspects of this RSA system. Okay. And currently there are a lot of developments, right? So what are some modern developments in cryptography? Some terms you would have heard: Bitcoin, blockchain. These are all about secret way of transactions and things like that. So I don't know anything about any of them. So I hope this won't be recorded. Okay. So before this public key cryptography, how was secret communication happening, right? So I want to convey some message M. I want to make sure an intruder doesn't see it. So I will apply some function f and send it to you, right? I want to send some message to you. I will take my message and apply some function, something, I will modify it, and you will see it. How will you retrieve the message? You have to apply the inverse function of it, right? So you should have the inverse. Okay. So what you will do is you will get this, and then you will apply some inverse function, and that's how you will see the message, right? So for example, can somebody tell me what this is? Hello. Okay. He found the message, right? So I showed an f of m. I did not even tell him f. How I constructed, he told me it's hello. Why? What is my function f? I just use the next letter for every letter. This is H, this is E, L, L, O, right? So this looks like some ununderstandable message the way he said, but a person who knows what I have done, you can retrieve the message. Okay. Now, I didn't even tell him F, and he managed to retrieve it. So this is one problem with this private key cryptography. So there were earlier, before public key, there were private key. There were two little problems. One is that key exchange. So what is this key key is roughly this function, okay, some key which I applied to my message, and I apply it so that nobody understands it, but the receiver should understand it, right, because if nobody understands it, the purpose is not solved if the receiver also does not understand it. So, I have to exchange this secret key with the receiver first, right. So, if I want to send some message to him, we both meet in a room and say, okay, this is how I am going to transfer messages, this is my function f. So, whenever you get this, this is how you apply f inverse and understand it. So, there is a key exchange which requires people to meet and transfer the key, right, meet, or because the inherent assumption is that any channel is very insecure, whatever way you send it, right. So, I could send the key over email, but then that is also insecure. I mean, if I believe the channel so much, I could send the message also in an unencrypted fashion. So, one is the key exchange, the other is that threat of attack, which means that often, for example, if I am sending a large text, the early cryptographic messages will do some little translations of the text and send it. Now, so retrieve message. So, what I mean is, it is not some, when I say attack, I mean crypto attack. What does that mean? That I did not even send the message, the secret key, and he already figured it out, right. This happens sometimes. There is this big message, I send it. What you can do is, you suppose, I mean, it depends on the function I apply. What you do is, you look at, do some text analysis. What is the most frequent letter in any English passage, do you know? T, right. So, what you do is, in my f of m, just do some analysis of the text and see what is the letter that is appearing more frequently, and you can guess that that is my f of t, right. I have translated t into that message, and then you can do similar kind of a lot of attacks to actually retrieve the message without even knowing the function f. So, this was another problem, and in fact, I mean, of course, you can complicate your translation function, and people became famous for not developing a crypto system, but for attacking the crypto system, right. So, usually, right. So, there are lot of different attacks on, so there were two problems with this. So, one needed way, so we wanted to, the key exchange problem was also that, think of a banking communication or just some email communication. I want to send messages to 100 people, right. It's infeasible for me to meet each one individually and exchange this, and then after some time this thing may go away and all that kind of thing. So, imagine, so what you need is some way of avoiding the key exchange. Somehow you should be able to figure out the f function and retrieve the message. Okay. This looks very counterintuitive. How would you do not even know what I applied, and how do you even be able to retrieve it. Okay. So, somehow will we come up with a system where we can avoid this exchange of the secret key. This is one thing, and the second thing was this attack. Now, we will base it on some computational problem. Right, somebody the other day was talking about passwords based on. So, we know NP hard problems, we know problems which are not solvable easily, that any brute method to solve them take exponential time, and those are good things to base your crypto system based on, so that an intruder cannot attack, because a way to attack may involve you to solve this hard problem, which will take exponential time. So, somehow these are some high level ideas, I am just motivating, and then we will get to the details, right. So, this power of the crypto system now is going to be based on some computational problems, hard computational problems. Okay. So, in particular, what we want is what are called one way functions. That functions which I can apply the f of m is easy to compute, but f inverse from f of m is hard to compute. Some functions where you can compute f easily, but the inverse is hard. Okay, we want to first come up with problems of this type. That is a sort of a solution to the second thing, and then we will see how to deal with the key exchange problem. So, let me give you a couple of examples of one way functions, right. These are going to be useful in this crypto system. So, for example, one way functions, right. So, I take two large numbers and multiply them. This is a one way function. I can multiply easily, right. It is a very easy function. Take two numbers, I can multiply. Now, what is the inverse? Yeah, factoring. Given this large number, can I factor it? Can I find the two numbers that gave me this product, right. So, for example, I take these two large numbers is P into Q. Okay. So, given P and Q, I can compute P into Q, but given P Q, if I want to find out P and Q, that is not easy. This is a factoring problem. We discussed about the prime problem of testing whether a number is prime or composite, and I said testing whether a number is prime is polynomial time solvable now, but if I know that it is not prime, but I want to find its factors, the brute force algorithm will be test 2, 3, 4 up to square root of n, right. We saw that even for the primality, that will take exponential time, right. That takes square root of time, square root of n time, but that is exponential. Why? Exponential in log n. Log n is the input size, right. So, that currently there are slightly better algorithms than that brute force algorithm, but all of them take exponential time. What is exponential in the size of the number? Okay, good. So, here is this is one function which we will really use it. We will take large primes, they are really about current primes on which crypto systems are based on, takes about 1024 digits. 2024 digits, we will multiply them, and that is what we will use them. But for inverse, factoring will take exponential time. Okay. I have not told you how to use these functions to build a crypto system, which will get that. Okay, that will be the climax of the talk, but I am just saying that here is an idea of dealing with this problem. The second one way function we will use is that f of m comma e would be m power e. Okay. So, first of all, let's also make clear that all our messages are going to be numbers. For the sake of this discussion, it is convenient to assume it, because you may actually want to send a 2-page document, convert them into ASCII, convert them into binary and all that, finally you get a number, and that number is what is being converted. So, it is much easy for this discussion to think of the messages as numbers. So, I want to compute m power e. Okay. How many multiplications do you need to get this? E multiplications, start from m, m square, m cubed, m power 4, m power e. Is there a faster way to do it? E by 2. How? Okay. So, what he is saying is, why only, why do you want to do? So, I can do from m, you can do m square, then I can do m power 4, m power 8 and do it, and eventually you might cross e or go up to the highest power of 2 less than e, okay, and then you come back and fill up the remaining thing, right. So, m power some 2 power k, because e may not be a power of 2, and then you need to multiply a few more things to get m power e. How many multiplications does it take? Not e by 2, log e multiplications. Why? This is like a binary search, if you think about it, right. This is doubling binary search. This is called doubling binary search. You start with 1, 2 square, 2 cubed. So, I do k multiplications. Okay. To get to up to this point, I am doing k multiplications. Suppose 2 power k is equal to e. What is k? Log e. If 2 power k is e, then log e multiplications, right. And then I may have to patch up for the remaining number of multiplications. So, that is also like at a 2 log e. Okay. A nice problem you can think of related thing is, suppose you want to do a binary search on a sorted array, but I do not tell you n, I do not tell you the endpoint, I do not tell you the size of the array. How will you do binary search? You will do exactly this. It start from 1, 2, 2 square, 2 cube, and suppose you know when you have crossed n, right. So, maybe you have an array where there are some junk elements and you know when you hit them, then you just go up to the next power of 2 and then you go and do binary search within that. So, that will take you only log of n. Okay. So, this is so log of e is good because it is polynomial in the input size which is of e. So, this takes computing this actually takes log e multiplications, okay, because that's good because that's poly in the input size, linear in the input size. But suppose I give you m power e and e, can you compute m fast? Okay. So, given, so that is the inverse function, right. Given m power e and e, can we compute m? How will you compute m? So, I tell you here is a number, okay, let us call this some n, and I tell you that n is a, do I even have to tell you a e at all? Yeah, okay, fine. Yeah, so I tell you that n is eth power of some number and I want to compute that number. How will you do it? Can you think of an algorithm for it? So, n is some m power e and I want to find that m. Try something, right? You can take log, okay, no, but that is not, we do not want to compute log here, we want to compute m combinatorial, I mean numerically, right. It is not a hard problem actually. How will you do? You just guess. I will just simply try 2 power e. Just try, okay. I will take 2 and see 2 power e and see whether that is equal to n. If it is not, if 2 power e is less than n, try 3, try 4. That will take m steps, but I do not want to take m steps. Yeah, do binary search, right? Exactly. I start from 2 power e, and if 2 power e is less than my number, then try 4 power e, 8 power e, 16 power e. So, I am doubling. So, this is like a log computation. The moment I go above n, then I know this range where it is and I will do some binary search there again. So, in log of many steps I can actually compute, if somebody gives me n and e, I can compute m also. Okay, in log of m many steps. However, this is where things get interesting. I am not going to do just m power e, because we are going to live in this world of, I mean, my messages are all, let us say some in this, let us make some assumption about my message space. Let us say 1, 2 up to m star, some huge big number, and this is where I am exchanging these numbers, right. So, now I pick some number from here and I pick another number e and I am taking an exponent, it may go beyond this m star. So, I want to bring it down. So, what do I do? What is a natural thing to do? Modulo arithmetic, right. So, what really I will do is that my f of m e is actually going to be m power e mod m star. Okay. So, I will come down to mod m star here. Now, here I can't do this binary search. Once I come down to m star, modulo m star, why not? Because it is not monotone. basically m power e mod m star. I know that as m increases, m power e will increase, and that's what I used to do my binary search, right? If I go up, I can come down. But when I do mod m star, there is no such monotonicity property. So the numbers can go, m power e mod m star may go up and down. The fact that m power e mod m star is bigger does not give you any clue about should I go up or down to guess my m. Okay. So here in this world, this is called discrete logarithmic problem, where I want to compute m. The only algorithm we know is pretty much the brute force algorithm of trying each possible value of m.